So yes, this session will be recorded and it will be available after the live session. Can anyone hear me? Okay, so before I begin, I want to send a link to invite you to join the IEEE UTD Discord. And if you scroll down to the channel list, you will see Review Room 2. And once you join, you will be able to share your screen and ask your question so I can answer them. Okay, so let's start. So in this review, I will be covering the following topics listed here. And I'm sure a lot of you already know the fundamental digital logic, the truth table, and the basic logic gates, and or, XOR, and inverter, those kind of gates. And we will also be discussing SOP, POS. And before I move on, I want to ask if there's anything specific about this topic you want me to cover. Oh, good. So let's begin. So for fundamental digital logic and truth table, let's start with AND gate, OR gate. So we know this is a 2-input AND gate here. And let's say the input X, Y, and the output is F. The truth table will be X, Y, F. And we start from 0, 0 to 1, 1, right? So the only output that's a 1 here is the last one, where both are 1 because this is an AND gate. Oh, you wanted me to cover decoder and multiplexer. Yeah, I will certainly cover that since I know a lot of you have questions regarding that. So next one is the OR gate. So again, XY input, function 0, 0, 1, 1, 1, 0, 1, 1, 1 as the OR gate input. Verilog? No, Jeremy. Don't do this to me. Yeah, so this is the truth table we called here, and this is your AND gate, OR gate. And I'm sure this is all just too simple for you, and I will move on to POS and SOP. So we have an example, let's say f equals to sum of term 0, 1, 2, maybe 5. And let's stop here. So we know that this will be a 3-bit variable, 3 bits input, right? So x, y, z, and let's define the z as LSB and the x as MSB. And we will be able to see that f equals to, look at the 0 term, this term first, we will have x naught, y naught, z naught, or, and then look at the 1. Here, we will have x naught, y naught, z, and the next one will be x naught, y, z naught. Y naught, z. So this is the 5th one. And after this, we can take a look at the sum of max term. And let's say this is, and then let's take a look at the K-map as well. 5. And so this is the 3 variable input. So we will have a 3 variable K-map. Let's define the top one as YZ and the bottom, the left one as X. So we'll have 0, 0, 0, 1, 1, 1, 1, 0. And this will be 0 and 1. So we know that at 0, 0, there's a 0 here because this is the max term. And then at 1, we will have 0. And 2 will be here. And 5 will be this one here. And then in order to simplify this, we can group a group of 2 here, right? And then another part here, a group of 2. And now I know that Dr. Nikoubin introduced something called a hazardous circuit. Does anyone have any question about the hazardous circuit? So from this K-map here, we can get the equation as follows: x naught, and since y is the one changing here, z will stay the same, which is z naught. Or let's take a look at this loop now. We will have y naught z because x is the one changing. So for Dr. Nikoubin's lecture, there's a section dedicated to this hazardous circuit, which we have to group this one in order to eliminate the hazard. So this is the Boolean equation with hazard. And then for the third additional loop, we will have a hazard-free circuit, which is X. So let's see, this is X naught and Y naught. This one is additional to eliminate the hazard. So, is there any question regarding the SOP and POS? Okay, and let's move on to the next topic, which is, yeah, so for the hazard, we know without the additional loop, the red loop, oh, sorry. The red loop here shares no common zero with the blue loop, right? So in order we want to connect the loop together, so we just we just have to add additional loop to group them together. Maybe the green one. So this is the green loop here. Well, because for the simplified circuit, there's going to have some timing issue due to the gate delay. And adding an additional loop to connect loops that are not connected together will be able to not eliminate the hazard totally, but it will eliminate some hazard. Is that clear, Adele? Okay, great. So I believe the next topic will be Quinn-McCloskey, right? Does anyone have any question regarding the Quinn-McCloskey, like a specific question? Okay. Let's move on. So the purpose of doing Quinn-McCloskey is because for the K-map we can do 4 variable and 5 variable, right? And 5 variable is just a 3D K-map. And for the inputs that have the output that has more than 5 inputs, you will be able to use Quinn-McCloskey to solve them, which is Let's do an example here. So let's do number 3 for now because it's the fastest one. So we have f equals to, no, this is the 4 variable one, so x, w, x, y, z. Let's define this as LSB, and this is MSB. So we will have wx, y, z. I see, and is it not shared? Cannot see the screen. Oh, I apologize. So can you see it now? Okay, great. So I'm doing the Quinn-McCluskey. If everyone is comfortable with this method, and then I will just move on because this will take a while. And I know many of you have questions regarding the multiplexer and decoder. Anyone wants me to keep doing this one? You're good with this? And is there anyone who wants me to cover Quinn-McCluskey? So how about the NOR configuration? No? Okay. So let's move on to Pos and Decoder. And then if there are people who has questions regarding the multi-level gate circuits and or Quinn-McCluskey, we can come back. Oh, the transistors. So for the transistor, Adele, we know that for a NAND gate, we have 2 PMOS and 2 NMOS. Can you see it now? Okay, so for the NAND gate, we have 2 PMOS and 2 NMOS. And then the next one is the NOR gate, which is also 2 PMOS and 2 NMOS. And in order to make this into an AND gate, we simply add a inverter at the end of the NAND gate. So we know that the inverter takes up 1 PMOS and 1 NMOS. So this will be 3 PMOS and 3 NMOS, right? And then same for the NOR gate. And if we add another input to each of the gates, we simply add 1 to each PMOS and NMOS. So take this as an example for 3. So we can derive an equation for this PMOS, number of PMOS. NMOS equals to 2 plus number of inputs minus 2. So for this equation, we can find out that if the input is 3 input, then 2 plus 3 minus 2 equals to 3. So we know that PMOS has 3 and NMOS has 3. Is this part clear? So let's take a look at the Boolean equation just to test it. So let's say we have A or B or C and end or end it with maybe D or E. Let's say this is this. So now we can see that this is a NOR NAND configuration, right? So when finding out the input of the NOR gate, we want to look at the number of terms here, which is 3 input. So 3 input NOR, it has 2 plus 3 minus 2, which is 3 PMOS, 3 NMOS. And for this gate here, two input NOR, we have 2 plus 2 minus 2, which is just 2 PMOS and 2 NMOS. And then the outside we have a NAND gate that is 2 input because it's NANDing these two terms together, so it's only 2 inputs. NAND, which is the same as this previous one. So is this part clear? And if any one of you has a specific Boolean equation you want me to solve to find the number of transistor for, please let me know. So I'm going to move on to the multiplexer and decoder next, if you don't have any question about the transistors anymore. Okay, so before we do this your homework, we have to understand the basic principle of the multiplexer first. And let's take 2 to 1 mux for now. There's an F, and usually at the top it will have address 0, and this at the bottom is your MSB address 0, and this is your address 1. So since we only have 2 inputs, we have only 1-bit selectors. Now whenever S0 is input 0, it will select this input and pass through F. And likewise, if I input the 1 into a selector, we will select this input from here and pass through the output. And let's take input X here as an example, and Y here as at address 1 as an example. So at the output F, we can, according to the concept of the mux, we can derive a Boolean equation called X is 0 not, or Y as 0. So let's say S0 and F and 0, 1. If S0 is 0 and inputting into this will be the inverse of 0, so it'll be X ended with 1 or Y ended with 0. And then we will know this is just X, right? And then for 1, we can say that this is X ended with 0 or Y ended with 1. So this is just Y. So this thing here, this Boolean equation here, applies to this mux. And then now we can start doing the problem here. So in this one we have a 4 to 1 mux, which means we will have 2 selectors because 0, 0, 0, 1, 1, 0, 1, 1. We have 4 addresses. So this address will be your address at this location, which is address 0, and this address will be at your 1 location, and this will be 2, and so on. So from this point, we can apply the concept we learned from the 2 to 1 mux and then derive an equation. So we know that f0, this input here equals to a. But in order to call this input to f, we have to have dc as 0. So d naught c naught. So at address 1, we know that a is inverted and then input into the OR gate, and b is inverted and input into the OR gate. We can know that f1 equals to, don't forget the parentheses, because this is entire input going to the mux. So we have a naught or b naught. Now, in order to call this address, right here, we have to have d as 0 and c as 1. So which means we can find this output as dc and d naught c. And then we do the same for this input. We know it's a 1. It's high input into that. So we have to end it with d equals to 1 and c equals to 0 to call this address. So d c naught. And for the next one, we don't even need to worry about dc, because it will always be 0, right? Because the 1 inverted, so it will be 0. And from here we can get the final function as a d naught c naught, or d naught c or d c naught. Does this make sense? Okay, so one of you said yes, and how about the other? Any questions? Yeah, Jeremy is the former head tutor. Take out the equation? What do you mean by take out the equation? You mean the previous? Take out the function. Still don't understand, sorry. Can you take out the expression? Sorry, I'm still a bit confused. You mean this? So your output will be this, right? So any question about this output? So let's move on to B. Does anyone still have any question about how to do muxes? Do you want me to do more? So now let's talk about the decoder. We can see part B. So Kyle, so I'm going to move on to decoder first, and to go through the concept real quick, and then we can do part B of the mux. So we know the definition of the decoder is based on your input here. You will have certain number of outputs. In this case, we have 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So let's number them. The top one will be your LSB. So 0, 1, 2, 3, 4, 7. And this will be your input, 0, 1, 2. And then, so according to this problem, we have an enable here. So the the purpose of the enable is if we input the input the 1 into the enable, it will actually be 0 inputted into the enable, because there's an invert here. So when the enable is 0, that means it's disabled. But if we ignore the invert here and just directly put here, we will have 1, and then it will be enabled. Now let's number this input as C be A. So we know the decoder is going to output a 1 whenever there's an ABC value inputted in there, and at address 0, ABC has to be 0 for this one to be 1, and the rest will be 0. So from this, we can know that this will be our output, A naught, B naught, C naught. And the next one will be A naught, B naught, C, because it's 0, 0, 1, and it's at address 1. And at address 2 is 0, 1, 0, so A naught, B, C naught. At address 3, we will have 0, 1, 1, so A naught, B, C, and we can go on. And when we apply this concept, we can then go to do the decoder part. So we know that this line here from address 1 is connected to F. But we have to take note that there's an invert here. And if I draw another decoder without the invert, this output here, we will have B naught C. And there's another one at 3, which is just BC. But since we are adding another inverter, because of this circle here, we have to do B naught C invert, and we can apply De Morgan's theorem. We will get B naught naught or C naught, which is B or C naught. And then we apply the same concept for address 3. BC naught equals to B naught plus C naught. And also we have to take note that there's an enable here with an inverse. So whenever A is 0, we have this circuit enabled. And this is a double invert here. So whenever A is 1, we will have this circuit enabled. So by adding the enable to the decoder, we can find out there's an equation here saying B C naught A naught, right? So if A is 0 and then invert of A, we will be able to enable this output out of the decoder. Anyone has any questions so far? Okay, so let's clear this. So we know this is B or C naught, right? With enable, which is A naught. And then this one, I'll put here. We will have B naught, C naught, and with the same enable, A naught. And after knowing these output, we can then move on to the next one, which is this one. So this output without the invert is BC naught. But if we invert it, it will become B naught or C. And then we don't want to forget the enable. So enable here is double inverted. So this will just be A. So whenever A is 0, it will actually input enable as 0. And whenever A is 1, the enable will be 1 for. This is for A equals to 0. So after finding out these outputs from the decoder, the rest are pretty easy because this is a 3-input AND gate. So F will be B or C naught, A naught, B naught, C naught, A naught. And then end it again with B naught, C, A. Does this part make sense? And if I'm doing anything wrong, please feel free to correct me. Okay, so we can then do part B. This is the mux again, and then we can apply the same concept of the 2 to 1 mux. So we have D as input into the address 0 here. So at address 0 for the output, we will get D and C naught, B naught, A naught, and at address 1 it's input 0, so we don't even need to care about it, just 0. At address 2 still 0, so F2 will still be 0 as well. And for 3, 4, and 6 is 1. So output at 3 will be 1 ended with C naught, B naught, A. I mean C naught, B, A. At address 4, we can get 1 ended with C, B naught, A naught. And for 5 is 0, so F5 is 0. At 6 is 1, F6 equal to C, B naught. Sorry about this. CB, A naught. And then at address 7, we will have 0. So F7 will equal to 0. So from these, then we can combine the output and get F equal to or C naught BA and the last one is CB A naught. Is this one clear? So what problem do you want me to do next? Anyone? So now we can try to do the 2-bit binary comparator, which is utilizing the concept of decoder and muxes. So we know that for a 2-bit comparator, let's say the first 2-bit is A1, A0, second is B1, B0, and then from this we can draw the truth table, which is sorry, bear with me for a second. Zero, 1. So after we finish the truth table, we can then figure out the definition of comparator. Comparator is going to tell you whether a bit is equals to another bit or it's greater than or less than, right? So we should have 3 outputs. Let's say this is equal, and the next one will be greater than. Next one here will be less than. So for equal to, we have the first one, O0, so this is equal, right? And this is 0, 0. And the next one will be, let's define this as A equal to B, A greater than B, A less than B. So then this one will be A less than B, so 0, 0. A less than B, less than B, greater than B. This is equal to B because 0, 1, 0, 1. This is B greater than A, which is A less than B, so which is this one. The next one will be A less than B. This is A greater than B. This is greater than, equal to. This is less than. And this one here is A greater than B. So here, still greater than, greater than. And this one will be equal to. After finishing this truth table, we can start by looking at individual function, individual output function. So equal to will be this at this spot, and then the next one for equal will be at this spot, which is A1, sorry, A1, A0. Oh wait, sorry about this. I forgot to include a B. B1, B0. They're all not. Or A1 not, A0, B1 not, B0. Or the next one is this one, which is A1, A0 not, B1, B0 not, and the last one will be all ones. So this is your output function for your equal to, for A equal to B. And let's look at A greater than B. So GRT equal to, know that there's a 1 here, so A1 not A0, and this is B1, B0 both not, and then find the next one, which is this one, so A1, A0 not, B1, B0 not. Next location will be this, A1, A0 not, B, B0. Next one is, which is A1, A0, B1, B0 not. This one will be A1, A0, B1 not, B0 plus this one here will be A1, A0, B1, B0 not. So this is now your A greater than B. So we do the same for A less than B, but to save time, and we can just do equal to first. So the problem 3a is saying that using the decoder 4 by 16, so this is your input 0, 1, 2, 3, LSB, MSB. So this is your 2, 3, 6, 16. So this is your 0, 1, 2, and all the way to 15. So there's only a place for input, which is this place, and we know that we have inputs A1, A0, B1, B0 because we want to compare them. So we can choose a random spot saying that this is A1, A0, B1, B0. The choice for this position doesn't really matter, but for convenience we can do to match this equation here, we should put A1 as the MSB, A0, B1, B0. So from previous problem, we know decoder, a 2 to 4 decoder is, let's say this is AB. We have 4, 1, 2, 3, 4. We know at this address there's an output of A naught, B naught, right? And then because this is basically address 0, 0, 0, 1, 1, 0, and 1, 1. So we have A naught B here, A, B naught, A, B. So we can apply the same concept for this. We know the first one will have A0, B1, B0, all invert. And then the next one we will have, this one should be 0, 1, 0, 1, which is 5, right? So 1, 0, 1, 2, 3, 4, 5. At this point is A1 not, A0, B1 not, B0. And the next one will be 1, 0, 1, 0. So which is 8 plus 2 is 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This one. Not. B1, B0 not. And then last one is just 15. This one's easy because it's all 1. So if you remember one of your homework problem, there was a connection like this, and then there's an OR gate, and basically this will be your output, right? So basically we can do the same here. We want to connect this, and this one. Pass through here and all into the OR gate. So this function here will be your equal to. So does anyone have any questions? So I assume you know how to get the greater than output, right? And less than as well. Yes, that's correct, Kyle. Okay, so let's do the max problem. Let me erase this. Oh wait, I just erased all my truth table. Don't want to do that. Sorry about that. Okay, the only part we need to delete is this one. Yeah. So let's take equal to as an example again. We have A to 1 marks. So we have select 0, select 1, select 3. We have 3-bit selector because we have to select a total of 8 address. So let's say we can choose a random input as our selector. And it really doesn't matter which one you choose. So in this case, I'm just going to choose A0, B1, B0. So by applying the previous Marxist concept, we have 2 to 1 marks, and this is selector, and this is A, B. So F will be A S naught or B S, right? And applied to this problem, we can have, give me a second. So it's pasting, and if A0, B1, B0 are all zeros, we want the selectors to output A1 not, right? Because according to this function here, so we can write A1 not into this address. So what if we have the next one is 101. When this is 101, we want this address here to have this input. So this is your address 5, which is this one. So A1 not. And it's the same for this one. Which is 0, 1, 0. This is address 2. At address 2, we want to have A1. And when this is all equal to 111 for the address, we want it to output A1 at this address. So for this mux, we only can have one output function, which means we will require a total of 3 other muxes for greater than and less than as well. Does it make sense? So if no one wants me to finish the greater than less than, we can start with part C. Anyone wants me to do part C? Okay. And then let's do part C. So for this, we are given the full adder blocks and minimum number of logic gates, right? So let's assume we are given this adder here. This is your A1, A0. This is your B1, B0. You're carrying. And we will have a sum of bit 1, sum 0, sum 1. And this will be your carry out. And in this case, there's 5 total inputs for the adder. But we don't need to use that many because we only have 4 inputs here. So carry in will just be 0. And then from this we can start the truth table for the adder. A1. Well, actually let's do let's use this one as our let's use this truth table as our adder truth table. Just to change something. So we have to rename this as S1, S0, and 0 will be your carry out. And then since this is an entire different component, now we have to change the entire output. My laptop is not working really well right now, so let's start with 1 bit, A0 and B0. And this will be your sum 0. This will be your carry out. So we start by 0, 0, 0, 1, 1, 0, 1, 1. So we know the sum for the first row will be 0, carry out will be 0. And B0, since this is 1 here, we have the sum of 1. And carry out will still be 0. This will be 1, carry out still 0. And this thing here is 0 and carry out is 1. So from this we can say that this is A0 equal to B0. This is A0 equal to B0 as well. And this is A0 less than B0. A0 greater than B0. So using this relationship, we can then draw a function that's equals to A0 not B0 not, or sorry, wrong one. We can then look at the output of the adder and see the S0, C0 are both not, or S not, S0 not, S1. From this, we can say that A0 equals to B0. So for greater than, we found that although a0, this one here is a0 greater than b0, and this one is a0 less than b0, they both have the output of 1, 0. So in order to fix this problem, we have to take one of the input and see the relationship between them. So if a0 is 1 and s0 is 1 and c0 is 0, this will be a greater than b. So next one will be less than. We do the same, but this one we can use b0 is 0, c0 not. And then we can draw the entire adder. This will be your b0. This is your a0. Cin, and the 0 s0, c out. So from this equation we can see we can design another circuit here, and let's inverse both output, and f equal will be s0 not ended with c0 not, and here's another output which is s0 not, and oh, I apologize, I keep making mistakes. So this will be your C out. And then we connect the C out to the AND gate. And then when we OR them together, this will be your F equal to, right? And stay A0, B0 here. And then we do the same for F greater than and less than, but we have to include the input into our logic gates here. So by applying this concept, we can be able to do the more complicated one, which is the 4 input one. Anyone has any question? No questions, but does it make sense? I hope I'm not confusing more people. For Dr. Nikoubin's course, he's going to teach you the concept of every logic gates, and then from those logic gates you can make more components like adders, muxes, and decoders. And using the concept of muxes decoders, he is going to ask you to design and apply those concepts to more complicated problems. K-maps and prime implicants. Okay. So we have, let's say, we have 4 inputs, w, x, y, z, and then let's say the sum equals to f, and let's say the sum of product is, say, 0, 1, 3, 7, 10, and let's add some don't cares, which are 15, 4, 13, and 15. Full adder. Okay, so I will go over full adder after the K-maps. So we can draw a K-map for four variables, and then we can choose one. Let's say this is wx and yz. We have 0, 0, 0, 1, none, last, both, first, no, last. So we can see that this is 0 here, right? And C, this is 1, and this will be 2, and this will be 3, 4, 5, 6, 7, and seven, and this will be 1, 1, which is 12, and 13, 15, and this is 2 plus 2, 14. So then we can add this, fill this out using the minterm 0 at location 0, 1 here, 3, 7, 10 here, 13 is the don't care, which is this one, 15 here. So actually the don't care here doesn't help. So let's say this is 2 and 4. 2 and 4. So we have let's not do 4, let's do 8. 8 would be better. 8 will be here. So we want to group it as 1 or 2, 4, 8, right? 2 to the n. So we want to group it large, as many as possible. So in this case, we can only group a 4 here, and this will be your W naught, X naught, because all these values here are changing. So W naught and X naught are the only one that's not changing. And then we can group another one, which is this one here. So we can see that W naught is not changing, and Y, C. And then there's another one, we can group it as a 4, which is this one. So W is changing, X naught is not, and Z naught is not changing. So this is your full adder, but as you can see here, this is has this equation. It's because all the loops share at least one of the ones with each other. Does anyone have any questions about this? Any more questions? So I know that someone asked me to go over full adder, right? I don't know if Dr. Nikoubin is going to include it on the test, but do you want me to go over the internal circuit of the full adder, or adder in general. Okay, I guess that's a good thing. So you don't even need to know part C then. Part C of this problem then. Okay, so I still have 17 minutes left, and if anyone wants to send me a question, please go onto the Discord. Please go onto the Discord link, and I will be able to see your question. And I'm going to paste this. Yeah, I can certainly go over full adder if you want me to. It's just that I don't know if you want me to go over the internal circuit, the logic gates inside the full adder, or the full adder and then the truth table of the full adder. Yeah, it will be available over the weekends. It's just maybe not Saturday morning. But please come to the tutoring room, because it feels really weird to not hearing any feedback while talking, and I'm not really used to that. Well, I hope this review session is somewhat helpful for you. And okay, no questions. So this is the first time for me to do YouTube Live, and a lot of things are chaotic, including my PC's fan running. CPU is exploding, so it's really slow. So let me do full adder for the last few minutes. So we have full adder, which is B and A carry. This is the sum out. This is carry out. And we will see that AB, truth table with carry in. You can start from here as 0, 0, 0, 0, 0. Yeah, Discord will be better, right? But the idea was that if I send you the link and you will be able to join the review room too, and then while you're watching the YouTube stream, I will be able to hear your feedback. So this is S0 C out. So we know this will be 0, and since carry in is 1 for this one, this will be 1. And B is 1, so this will be 1. And this will be 0 because carry in and B is 1. So C out will be 1. The rest are 0. So this will be 1, 0, 1, 0, and 0, 1, and 1, 1. Yes, but no one joined the Discord, so I couldn't hear any feedback. Okay, so if you want to understand the truth table, then we can interpret it as S0 and C0 equal to A plus B plus Cn. So when A is 0, B is 0, C is 0, it's just equal to 0, right? But if 0 plus 0 plus 1, it will be 0, 1. So C out, S out, and 0 plus 1 plus 0. So this will be 0, 1 again. So if we have 0 plus 1 equal to, this will be equal to 1, 0, right? Think of adding in binary, and you will be able to find the output of the full adder.